Hi there, it's Mr. Harold here, and this video is going to be about activity and half-life. We're going to look at key concepts and definitions, half-life graphs, half-life questions, and using half-life to calculate the age of different things. Now, before we get started, you will need a pen, pencil, a bit of paper, and a calculator, because we will be doing some calculations and some division sums where you might need to use that. Okay, so first of all, let's think about what radiation is, or what radioactive decay is. And radioactive decay is a way that unstable nuclei become more stable. So for example, if we liken an unstable nuclei to a stacked bowl of grapes, if we keep stacking these and stacking these and stacking these, we fill the bowl up to a stable state. But if we keep on going, one of them will fall off. So that's a little bit like an unstable nuclei in terms of radioactivity. We can't guarantee when it will happen, but maybe it's the slightest knock, a little bit of extra energy or something like that, and one of those will fall off. And that's very much like radioactive decay. If we were to link that to a type of radiation, we might liken that to an electron in beta decay. However, that's not always the case. Sometimes we have more than one nuclei, and we could have something in terms of alpha radiation where we get 2 protons and 2 neutrons being emitted. Now, if we have a look at the picture on the right hand side, we can see there now that we've got more than one nuclei, and we know that if we stack them all identically, I know we can't, but imagine if we could stack them identically, there would be a chance that one or more of those grapes would fall off, and that's a measure of what's called its half-life. So if we were to think about over a period of time, so say 30 minutes, there might be a chance of 2 of those falling off, and the next 30 minutes there might be a chance of 1 of them falling off, and then in the next 30 minutes there might be a chance of the remaining 1, or possibly not happening, falling off. And that's the definition, or the explanation, or an analogy of what half-life is. Now, we have lots of different types of stable and unstable nuclei, and we can see that we've got some here. So this is all of the same element, and that is iodine, but these are different isotopes of iodine. We know that they're all iodine because they've all got the symbol I, and they've all got the same bottom number, that proton number of 53. Or atomic number, depending on which way you call it. However, what is different is the mass number, and we can say that the mass number of these are all different, and that's because to be an isotope it has to have different numbers of nuclei. So we can see that iodine 127, for example, is 100% stable. We'll have that, and nothing about it will change at all. Slightly less stable than that is iodine 129, and we can see that that has a half-life of 16 billion years. So in terms of stability on a day-to-day level, that is fairly stable. Is it 100% stable? No, but it's relatively stable. There's not going to be a lot of change going on there. And then if we have a look at the other extreme, we've got iodine 135, which has a half-life of 6.6 hours. So what that means is we would be predicting that after 6.6 hours, half the radioactive nuclei will be used up. So it'll give off its energy, it'll give off radioactive decay, and it will become more stable. And every 6.6 hours, it will halve the number of radioactive nuclei. Now, I tried to get these videos to play in here, but I couldn't work out how to do it. But please have a look at the 2 web links that I've given there. These are to a great website called PHET, P-H-E-T, which is linked an affiliation of the Colorado State University in America, and they have some great simulations on there for biology, chemistry and physics. And the 2 I'd like you to have a little look at are for alpha decay and beta decay, just to remind yourselves of what those are. So after looking at those little simulations, there are a number of key ideas for us to have a think about. One is that unstable nuclei emit radiation to become more stable. They don't like to be in this unstable state. They want to become more stable, so they give off radiation to do that. Radioactive decay is random and spontaneous, We don't know when it's going to happen, but we know the probability of it happening. That's our measure of half-life. And we measure the activity with the units of becquerel, symbol BQ. Also, in terms of half-life, you need to be aware of the following things. It's the time it takes for half the nuclei in a radioactive sample to decay. Or another definition is it's the time it takes for the count rate to half, or the time it takes for the activity to half. All three things are fairly similar and a good measure of that decay process and how long it takes. So, some quick questions. What is the process of an unstable isotope becoming a stable isotope called? Correct, it's radioactive decay. Now, this question goes back to previous lessons that you would have had when you were first taught about radioactivity in school. Which of these events can happen during radioactive decay? Have a little think about it. And well done if you realised it was all three. So, a neutron turning into a proton is a result of beta radiation. Lose 2 protons and 2 neutrons is alpha emission. And loss of a single neutron is neutron emission. What does the term activity mean? So option 1, 2, 3 or 4. Pause the video, have a read of them. And it was 1, the rate at which a source of unstable nuclei decays. Which of these words describes radioactive decay? Quite clearly, or hopefully, obviously, it was random. And what is activity measured in? What's the unit of activity? And as we just said before, it was the becquerel. Okay, and have a think about this question. An isotope of hydrogen has a half-life of 8 hours. This means that, so which one is it? Is it answer 1 or answer 2? Answer 1, after 8 hours, half the isotope will have decayed, and after 16 hours, 3/4 of the isotope will have decayed. Or is it answer 2, after 8 hours, half the isotope will have decayed, and after 16 hours, all of the isotope will have decayed? So have a think about that, think carefully, and then select your answer. And it was answer 1. Because remember what half-life is. Half-life is the time it takes for half the radioactive nuclei to decay. So after one half-life, 8 hours, there'll be half of it left. After another 8 hours, there'll be half of that half left. So you'll be left with 1/4, therefore 3/4 of the isotope would have decayed. And some questions for you to have a go at yourselves. Again, pause the video, have a read of them, try and work out the answers, and then resume it, and I'll go through the answers with you. Okay, so let's just go through the answers. So number 1, if the radioactive sample has an initial count rate of 600, what's the count rate after 1 half-life? It'll be 300. After 2 half-lives, 150. After 3 half-lives, it'll be 75. And after 4 half-lives, 37.5. The half-life of iodine is 13 hours. If a sample of iodine has an original activity of 400 becquerels, what will its activity be after 26 hours? Well, 26 hours is 2 half-lives, so that'll be down to 200 and then further down to 100. Another half-life after that will be down to 50, and then another half-life after that it will be down to 25. Again, some more questions for you to have a go at. Pause the video and we'll go through the answers in a moment. Okay, so let's have a quick look at the answers. So sodium-24 has a half-life of 15 hours. If the sample has an original activity of 800, what will be the activity after 15 hours? So that's 1 half-life, so it'll be down to 400. 30 hours, it'll be down to 200. 45 hours, it'll be down to 100. And 60 hours, down to 50. Again, can you have a go at these questions? So just pause the video and have a go at working it out. I'm not going to give you the answers for these, but it'll be a chance for you to do your own work. And another question for you to have a go at. Again, remember to work out the number of half-lives and then apply the fact of it halving each time. And on to some harder questions for you to have a go at. What makes this a little bit harder is the fact that we've got mixed units of seconds and minutes. So 75 seconds, after 75 seconds, the percentage left will be 50%. After another 75 seconds, which is 150 seconds, there will be 25% left. After another one, there will be 12.5, and another one, there will be 6.25. So it'll be 6.25% after 5 minutes, because 5 minutes is equal to 300 seconds, which is 4 half-lives. Okay, so next we're going to look at graphs of radioactive decay and how you can use those to answer questions. Okay, so first of all radioactive decay graphs have the same shape as this basic exponential shape graph, and that's because of the nature of the radioactive decay. So what is the time taken for the mass of the sample to decrease by half? So to decrease by half, we look at where it starts, and it starts off at 540. Half of that is 270, so at 270 I'm going to draw a line across to the graph, and then I'm going to draw a line straight down, and we can see that line that goes straight down is at about 2, 4, 6, 7 hours. So the time taken for the mass of the sample to decrease by half at 7 hours, therefore its half-life is also 7 hours. It's the same thing, it's the same definition. Next one, let's do this together. So what is the time taken for the mass of the sample to decrease by half? So again, have a look at how much it starts with, and then work out the half-life. Pause the video while you have a go at doing that, just by reading it off the graph, and then I'll go through the answers with you. Okay, so hopefully you got an answer. So the first thing we should have done is find out that the start graph is at 2,400. So we need to find half of that and draw a line across. So that's at 1,200. And then a line down. So if we know that the first block is at 10,000 years, each block of numbers each square is worth 2,000. So we've got 2,000, 4,000, 6,000, about 6,250 years. And again, that is the half-life, because that's the definition of half-life, the time taken for half the sample to decrease. Next, can you have a go at doing this yourself, please? Use exactly the same method that we've already used. So we're going to start off at 800, a line across at 400, and a line straight down. If each block of squares must be worth 40 seconds, so at 4, 8, about 120 seconds. And that's the half-life. And another one for you to have a go at, what would be the answer for this one? Again, pause the video, work it out, and I'll show you the answer in a second. So the graph starts at 124,000, so half of that is 62,000. So a line across, and then a line down, and if each of those, each square represents 20 days, we've got 20, 40, 60, about 70-ish days. Okay, there is often a scope for a varied answer, so there'll often be a range of a small percentage either way for the answers. So half-life can also be used to determine the age of things, and that's what you're going to have a go at doing next. So please read through the information that's on the screen, pause the video, and have a go at working out the question that's asked at the bottom there. Use the data to show that the oldest parts of the Earth's crust are about 4.5 billion years. So pause the video and have a go at working that out. Next question, again, can you pause the video and have a go at working out what's being asked? And another one, pause the video and have a go at working out the current activity of the carbon-14 in the leaf. Okay, and finally are some exam-style questions for you to have a go at. So there's a graph, same shape as what we've always seen. But again, pause the video and then try and work out, or try and answer the questions. So what is meant by the term half-life? What is meant by the term isotope? And the answers were as follows. So it's the time it takes for half the number of nuclei to decay, or the number of nuclei to drop by half. And the other one, it's the same number of protons but different number of neutrons. And use the graph to find the half-life of barium-133. Again, pause the video and have a go at working it out. And the answer is 10.5 years. Okay, so another one. This question is about nuclear radiation. Radioactive materials decay naturally. The half-life is a measure of how quickly the radioactive materials decay. Look at the data below about the activity of some radioactive isotopes. Which isotope has the shortest half-life? Is it A, B, C, or D? And can you explain why? Now the answer is A, and it's because the idea is there that the half-time is a type to reduce the count rate to half its original value. the idea that the half-life is the time taken to reduce to 3,000. That will get you a mark. But the idea that A reaches half its original value of 3,000 in a shorter time than the others. So again, 1 mark for saying what it actually is, and the other mark is for saying why it's A.